Hi class, this is Mrs. Lyons, and the purpose of this video is to help us understand how electrons are located in atoms and how we can represent that as we get into talking about chemical reactions and bonding and all of the other fun things that we are going to learn in chemistry this year. So to start off, electrons are found, we're going to talk about shells, subshells, and orbitals. Okay, so electrons within an atom are confined to a specific region of space, which is called a principal energy level. All right, electrons in the first shell, okay, first energy level, are closest to the nucleus, and they are the lowest in energy. The shells are numbered just with numbers 1, 2, 3, 4, etc. from the inside of the atom out. So the shell closest to the nucleus is energy level 1. These shell numbers correspond to the period on the periodic table. Okay, so going from top to bottom, period 1 is hydrogen and helium. Period 2 is lithium, beryllium, etc. Okay, so the energy levels correspond to the period on the periodic table. Within the shells, there are subshells, and these subshells have the letters S, P, D, and F. And these are the letters we will use to represent subshells. Okay, and within the subshell, there are orbitals. And an orbital is a region of space that can hold up to 2 electrons. All right, so let's look at what these shells and subshells and orbitals look like. All right, so the first shell contains 1 s orbital, and it can hold 2 electrons. Okay, the second shell contains 1 s orbital and 3 p orbitals. All p orbitals come in sets of 3 and can hold up to 6 electrons. The third shell contains 1 s orbital, 3 p orbitals, and 5 d orbitals. D orbitals come in sets of 5 and therefore can hold up to 10 electrons. And then finally, the fourth shell, the fourth energy level, contains 1 s orbital, 3 p orbitals, 5 d orbitals, and 7 f orbitals. All f orbitals contain 7. All f shells come in sets of 7. So that means that they can hold up to 14 electrons. All right. So if we look at this, and hopefully you see the pattern there, as you increase energy levels, each energy level has additional orbitals available. So if we think about this, okay, so we're talking about our shells. Shell 1, energy level 1, holds 1 s orbital. And we specify the energy level is that 1. The subshell is s, and it can hold a maximum of 2 electrons. All right. The second energy level, okay, has 1 2s orbital and 3 2p orbitals. Now, what I want you to realize is that as we go out, we said that they fill from the inside out. So if we're looking at an atom that has electrons in the second energy level, that means the first energy level would be full. So the second shell contains 1 2s and 3 2p orbitals. So if we add the 2 plus 6, the second energy level can have up to 8 electrons. The third energy level has a 3s, 3 3p, and 5 3d subshells, orbitals, okay? And we can hold 2 plus 2 in the s, 6 in the p, and 10 in the d for a total of 18 electrons in the third energy level. All right, within the fourth energy level, there are 1 4s orbitals, 3 4p, 5 4d, and 7 4f orbitals. So within energy level 4, we can hold up to 32 electrons. Okay, so that's going to be really helpful for us as we start putting these atoms together and seeing where the electrons are found. All right. Orbitals have a space. They have a shape, okay? Because remember, when we talk about orbitals, we aren't talking about, remember the Bohr model just has the orbits, it looks like rings around the sun. Well, that's not a realistic picture of what an atom looks like. What was found later on was that the orbitals are a space and they're a shape, and there's a probability of finding an electron within that shape. All right, so s orbitals are spherical. The nucleus is found at the very center of that first s orbital. P orbitals are shaped like dumbbells, and there are 3 p orbitals, and they're at 90 degrees to each other. And one orbital is on the x-axis, one orbital is on the y-axis, and then one orbital is on the z-axis. And then finally, d orbitals are shaped like double dumbbells, and they get really complex, so we will not even try to draw them. Okay, so there are rules about how electrons fill in orbitals. Okay, so when we're talking about where these electrons are, we need to know these rules. Okay, and this is in the ground state of the atom. Only the lowest energy orbitals are occupied. Okay, so the first rule, orbitals will fill in order of increasing energy from the lowest energy to the highest, so from closest to the nucleus on out. Rule 2, each orbital can hold 2 electrons. They have to have opposite spins. We represent this with arrows, one pointing up and one pointing down. And then rule 3, when there is a set of orbitals of equal energy, for example, we have 3 p orbitals, okay, they all have the same energy. Each orbital becomes half filled before any of them becomes completely filled. So we would put 1 electron in each orbital before we put 2 in any orbital. All right, so we do these orbital diagrams, and the orbital diagram has a box that represents the orbital, and then an arrow with its head up to represent a single electron, and a pair of arrows with heads in opposite directions to represent 2 electrons with paired spins. All right, so I'm going to show you how to draw these orbital diagrams. Okay, so for example, the first element on the periodic table is hydrogen. Its atomic number is 1, so it's got 1 electron. So we would start with the 1s orbital, and we would put 1 arrow in it. Now, we're going to write an electron configuration. That's an easier way to represent the electrons than drawing these orbital diagrams all the time. All right, so we would represent hydrogen as 1, energy level 1, an s subshell that contains 1 electron. Helium has 2 electrons, so now we would have a second electron facing the opposite direction. The electron configuration is going to be still energy level 1, still subshell S, but now we have 2 electrons, okay? And we're going to talk about something called the noble gas configuration here in a bit. I'm going to put it up here, and then we'll come back and talk about it in a couple of minutes. So let's do a couple more practice. So if you look at carbon, carbon has 6 electrons. So we start in energy level 1, 1 arrow up, 1 arrow down. Then we go to energy level 2. The s orbitals are first, 1 up, 1 down. So that's 4 electrons. Then we come to the 2p orbitals. Okay, remember there's 3 of them. So we're going to put 1 electron in each box before we double up. So there would just be 2 electrons, 1 in each of 2 boxes. The electron configuration then to represent this would be energy level 1, subshell S contains 2 electrons. Energy level 2, subshell S contains 2 electrons. And then energy level 2, subshell P contains 2 electrons. So 1s2, 2s2, 2p2. And then again, the noble gas configurations, we will talk about what we can do with this. Making it even easier is that we use the symbol of the noble gas in brackets, okay? And that's the noble gas that precedes the atom we're talking about, okay? And then what we do, the noble gas in brackets represents all of the filled subshells, okay, before it. So what we're doing here, we would replace the 1s2 with helium, and then just write 2s2, 2p2. And in this case, it doesn't seem like it's really that much of a shorthand, but we'll get to where it really is, where it really pays off. All right, so the next atom we want to look at is fluorine. Fluorine has 9 electrons. So we started out here with 1 electron in the 1s subshell. We're going to fill the 1s before we move on to the 2s. Okay, then we're going to put 1 up, 1 down in the 2s subshell. And now we're going to move to the 2p orbitals, the p subshell, the 2p orbitals. And here's where we're going to put 1 electron in each orbital before we start doubling up. So now I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so this is how we would represent fluorine with an orbital diagram. The electron configuration then is going to be 1s2, 2s2, 2p, 1, 2, 3, 4, 5, 2p5. Okay. Noble gas configuration. Again, we're going to use helium in place of 1s2. And then we just write what comes after helium. Okay, so let's look at silicon. Silicon has 14 electrons, and this is where that noble gas configuration is going to start to look way more handy. All right, silicon has 14 electrons. All right, so if I start, I'm always going to start with 1s. I'm going to put 2 electrons in 1s, 2 electrons in 2s, and then in 2p, I'm going to do 1 in each orbital before I put a second. So now let's see, I've got 2, 4, 6, 8. I've used 10 electrons. I have 14. So I'm going to put 2 electrons in the 3s. Now I move to the 3p. I need 2 electrons. So I'm going to put 1 in each box. I would not double them up until I'd filled that third box. All right. So now the electron configuration is energy level 1, subshell S, 2 electrons. Energy level 2, subshell S, 2 electrons. Energy level 2, subshell P, 6 electrons. Energy level 3, subshell S, 2 electrons. And then finally, energy level 3, subshell P, 2 electrons. So 1s2, 2s2, 2p6, 3s2, 3p2. Now, here's where the noble gas comes in handy. The noble gas that comes before silicon is neon. Now, if you were to write out the noble gas configuration for neon, what you would find is it's 1s2, 2s2, 2p6. Okay, so instead of writing all of that out, we just write neon, and then we write the end part of the electron configuration. Okay, so that makes it what that represents, the neon in brackets represents the noble gas and all of the filled shells that come before. All right, the last thing that we need to talk about today is what we call a Lewis dot structure. All right, so Lewis dot structures, the purpose of these and the reason that they're so handy is when we get into chemical reactions and bonding, the chemical and physical properties are a result of how many electrons are in the outermost energy level, what we call the valence shell of an atom. Okay, and we are going to use this electron dot, Lewis dot structure to represent just the electrons in the outermost energy level, just the valence electrons. Okay, so a Lewis dot structure shows the symbol in the middle, and it's surrounded by dots equal to the number of electrons in the valence shell. And when we write them in, it's kind of important to write the electrons in a certain pattern. We are going to put one. We're going to pretend that there are 4 sides to our atom. Okay, so this is kind of like the element symbol in a box, and then we're going to put 1 electron on each side of the element symbol, and then we'll add a second electron, okay? And that's going to become really handy when it comes time to talk about bonding. All right, so the the atomic symbol represents the nucleus and all of the filled inner shells. All right, now an important thing: elements. Okay, elements in the same group, in the same column on a periodic table, have the same ground state electron configuration in their valence shell. Okay, all main group elements. Okay, main group, we're talking about 1s, 2s, or we're talking about S and P, groups 1 and 2, and groups 13 through 18. Okay, when we look at those main group elements, they are having their S or P orbitals being filled. All right, so the 1s shell is filled with 2 electrons. Okay, we know that 1s, 2 electrons. Notice how many elements are in the first period on your periodic table. There are 2. The 2s and 2p shells can hold a total of 8 electrons. So energy level 2 can hold up to 8 electrons. How many elements are in the second period on your periodic table? 8. Not a coincidence. All right. For the main group elements, again, groups 1 and 2 and 13 through 18, the number of valence electrons are equal to the group number, except it's the group number minus the 1. Okay, so group 1 has 1 valence electron. Group 2 has 2 valence electrons. Group 13 has 3 valence electrons. Group 14, 4. 15, 5. Okay, so we can literally look at an element on the periodic table, and based on its location, we can tell how many valence electrons that atom has. Okay, so here is a picture of the first 20 elements. Actually, it's beyond the first 20. No, the first 20 elements on the periodic table. All right, so if you look, this is group 1, hydrogen, lithium, sodium, potassium. Each of them have 1 valence electron. Group 2, beryllium, magnesium, calcium. Each have 2 valence electrons. Now, when we notice that this is a little weird, we've cut out that middle transition element part of the periodic table just to fit this into space. Notice then, boron and aluminum are in group 13. They each have 3 valence electrons. Carbon and silicon are in group 14. They each have 4 valence electrons. Okay, so this continues. Now, there's a little thing you need to pay attention to when we get over here to the noble gases. Neon and argon they're in group 18. They both have 8 valence electrons. So why does helium only have 2 valence electrons? Well, if you consider the structure of helium, helium is atomic number 2, 2 protons, 2 electrons. So helium doesn't have 8 electrons. So it can't have 8 valence electrons. And it's just because it's up there in that first energy level. So helium has 2 valence electrons, and it is a noble gas. It's very stable with just 2 electrons. All right, so that is just a little lesson on how we are going to represent elements and the electrons that are going to influence their physical and chemical properties and how they bond. I hope this was a helpful video. Have a fantastic day. I will see you in class.